Welcome back. This is tutorial 9, modeling volatility 2, the second one talking about volatility. Let's start with a little bit of admin today. Hi, Minami. Yeah.
Hi.
Yeah, just started recording.
Yeah.
Yeah. And so quiz 3 is available. It will be available until I think next Friday, right? The May the 5th. Don't forget to click submit by the end of it, and it's worth the same as the ones before. But I'm sure what you have in mind this week will be our report 1, right? It's due this Friday. So from what I'm recording now, it's less than 2 days for the due date. So don't forget to submit it before 4 o'clock. So 3:59 is here, probably 59 seconds, but you don't want to play with that. We don't want to get too close to 4 p.m. And there are some late submissions. I added this little thing here if you submit it late. So be careful. Yeah, try not to miss some marks because of submitting it late. All right. And also feel free to join our tutorials and consultations if you have questions about it. And if it's tutorials, of course, you have to wait until the end of the tutorial, but we still have a few consultations until Friday too. In fact, I think all consultations is still, maybe one is gone past today, but that's it. All right, good luck with it. Next. What we have today will be some data from Merck once again. This is a smaller version. There's just a one-time series in this one. And feel free to download the tutorial PDF too in the same folder. Save it into a folder. And also, let's save this code into a folder in codeshare.io, same as usual. So 3350_09. Tutorial 9, that's the address. Let me see if I click that. This is what you should find. Somewhere around 300 lines of code and comment. So I will copy, open my R, then I'll create a new script, paste everything as we've been doing, and then I'm going to save it in the same folder as we have. I'm already in the right folder here. So I'll call it tut09 live. And that's it. Okay. Let me go back to the slides. So save your script in the same folder as you had the data set, and let's keep going. Today, we'll be talking about volatility again. But we'll be talking about some slightly different models than what we saw last week. So modeling volatility 2, by the end of this tutorial, we should be able to construct an adequate set of models with possible T-gauge or threshold gauge errors, construct an adequate set of models with possible gauge in mean or arch-M, gauge-M. You'll see with some different nomenclatures, but different names. But all right, gauge in mean components. So use R to draw inference on the presence of leverage effects from the class of T-gauge models, and use R to draw inference of the presence of time-varying risk here, premium from a class of gauging mean models. Use R to estimate and forecast volatilities based on models with T-gauge errors and gauging mean components. All right, that's a very good summary of what we're doing. But first, let's do a little bit of recap of what we did last week. I think would be helpful. We start by estimating an AMO model, and we suggested many. But after that, usually the AMO model, without thinking about volatility, you would have a constant variance, this assumption of a homoscedasticity. But sometimes we have some different variance depending on where we are in time, right? So we can't say anymore that we have a sigma square as a variance for the whole time series. So what did we do last week? We got the error or the residuals here, and we tried to put another stochastic model in our errors. So we put it out, we saved it, then we squared it. And look, this is a little bit of the format things take, but this is before squaring. Oop, let me take it off. You have a new t, which is just on a standard normal, which is normal with a mean 0 and a variance 1. Can also be represented at this distribution, or sometimes is represented as a z, as you've seen before. But okay, a standard normal times at the square root, which is this 1/2 here, of ht. And ht is where we put our model. I have clicked here already. So when you look at the arrow, squared is the same thing squared. So new t is squared here, and our ht, it's equals. For example, if we're modeling with just one q equals to 1, this arch model looks like that. And does it remind you something, having alpha 0 plus an alpha 1 in the error? Think about it. It does look like a moving average model, which was our regression here with just one leg of, which is q here, q equals to 1 leg of error. So we had our current error or contemporaneous error t, and also a t minus 1, which is here. But in this case, we're talking about residuals squared or errors squared, right? So pretty much our arch model is specified like that. You have your arm here, then you get your error, and you model it as a new t, and square root of ht, and here is the model you model that, right? So arch q would be just one leg. And can you see? I hope I try to put some different equations from the slides together so we can see the connection of what we're doing. Normal armor, take the error, square it, then try to model it, and this is what you end up with, right? So this was an arch model that looks like a moving average. Then what was the gauge model? Why the general autoregressive heteroscedasticity, conditional heteroscedasticity change? There's also a p value there. And I was telling you, it was like, oh, the gauge legs are here and the arch legs are here. It's a one way to think about it. But look at what we have new. When we squared our error, we're modeling the same thing, but the difference is now would not only consider the legs of the error, but we also add autoregressive legs of ht, which is nothing else than our autoregressive, nothing different from our autoregressive here in our ARMA model. So you see we have a ht, and now we're modeling with some ht minus j, for this j here on the legs. So that's why this part in here looks, I think it's pretty clear now, but think about what it looks like. Looks like an ARMA PQ, right? This guy looks a lot like this one. But this one is just talking about modeling the residuals. So in the equation, it would be the same as putting this guy in here. So we squared and model it like that. All right. So this is what we did last week, and we made some estimations. But what is new for this week now? Let's move. You see, in practice, the most commonly used is gauge 1-1. When we square our residuals, we are not considering if the residuals is positive or negative. We're treating both positive and negative the same way. So this here is when you have some news. I should have left a little bit more text there. But look at the gauge. We're saying, let's think, and I think this slide, I hope it makes sense why volatility is so important for finance and for people who wants to work with finance, which I would imagine a lot of the students in this course are. how relevant it is. The Garch model would give you the same impact for positive news or negative news. So let's think about the stock market. Let's say from yesterday into today, it grew a little bit. So some positive news. Look, if it grew by 0.5%, Garch thinks that the volatility would be running a little bit below 0.02, let's say 0.02, and it will be the same as a negative impact. So if it went down, stock market went down by 0.5%, it would have this 0.02 volatility. But we know that, in fact, when you look, usually investors tend to react way more, let's say, aggressively to, or emotionally, to negative news than they do to positive news. Actually, it's a little bit of an expectation. You expect the stock market to go up a little bit throughout time. So growing a tiny bit day after day, it's positive. Of course, it oscillates, but it's kind of expected. But when it goes down, particularly when it goes down a little bit too much, as you probably know by now, people freak out. And so they tend to react a lot to falling down. Some people will be betting that the next day will recover, so they'll also buy. So it's important to think that this is volatility or variance. This is amount of variance, and this can be positive or negative in our expectation, right? This is, I think I can't say it enough. We're talking about variance. So how can we model, if we squared here, how can we model this difference here, being negative, being way more important than positive? What we do is to use, there is the E-Garch, but today we will be using the T-Garch or threshold Garch model, and we do the following. We model our height T the same way as we did our Garch 1.1, for example. Here's just one leg of error and one leg of itself, autoregressive. But we also get an extra thing in there. And this threshold works a little bit like that. If the previous error was negative, then dt minus 1 receives a 1. So you see here, if the previous error is negative, dt receives a 1. So if the volatility or the variance from yesterday was positive, then the amount that our volatility will take from that positive one will be alpha 1. So just alpha 1 here, if it was positive. But if it's negative, we will take alpha 1, and we will also take this lambda. So this is supposed to be larger, and it's interpreted as the leverage effect. This is the leverage effect in our T-Garch. Okay. So for T-Garch, this guy is greater than 0. I think you notice that E-Garch, it's smaller than 0, but for this one, it's greater. And that's what we're doing for question 1. We will be modeling using this version here and testing to see if this guy is present, statistically significant, and etc. All right. So that's it. So let's go to our exercise. Consider the daily prices of Merck and Co. Once again, from the period of 2nd of January 2001 to 23rd of December 2013, in the data file CSV that we have. Let YT denote the process of share prices. Recall that we learned we now consider extensions of these models to capture the possible leverage effect and time-varying risk premia. So for the first one will be leverage effect for question 1. So first, let's load and plot our data, RStudio. So first I start just cleaning the environment, plots, and our console. Let me give it a little bit of a zoom. Yeah. Then, next thing, we're going to load forecast, deploy, and root gauge. Depending on when you load, if you see some warnings, a new version of R just came out. So if you feel like installing, you'll probably be able to find in CRAN R project. If you go there, download R for Windows, for example, is what I use. So 4.3 just came out now in April. So yeah, you might see some warnings. Nothing to worry about. Probably everything works the same still. Let me put this one together. So now, second thing, I'll set my working directory. It's the same as clicking session, set work directory to source file location, or choosing the directory where we're going to find the Merc file, Merc CSV. You will see I added to this line, Merc, there is a little one here, .csv, because I imagine that when you save the file, I think it's coming as a one, because we had a previous Merc that is a different name. But let me give it a go again. Week 9 tutorial Merc. Okay, it offers me, since I have it here, it will come with a open bracket 1 close bracket, just in case. If you save it with a different name, just add it here. But I thought I should call your attention because this one is coming as 1 in brackets. All right, so we loaded. We have 3,264 observations with 2 variables only, the date and the Y, the value of the stock. So we are creating a date variable, so translating whatever we have to the R language, so year, month, and day. Then we're taking R from our data set and saving it inside of this R. And finally, we're calculating the returns as we did before. So it's just the difference of the log values of Y. And there it is. If I put returns, you'll see much smaller numbers, which we can be interpreted as changes in percentage, right? So let's plot our returns. We could plot Y2 to see the prices, but we've done it in the past. Let's plot our R, the returns, and we will have this date -1 in there. Oh, it's looking very small in my screen. Let me try to expand it a little bit. But have a look how it is looking. Looks quite stationary, but you will see not really homoscedastic, right? You have quite a big cluster of volatility here, some huge spikes in here, and etc. So one important thing to think today is that look at the negative, how the negative is more negative than the rest. It's still volatility, but I think this is one way of calling the attention. And let's go. This is our plot of returns. Remember, we use this -1 here because we took a difference. So R has 1 less observation than Y and our data. All right, we got to this part. First, consider the class of ARMA PM, QM, and threshold gauge, PUH, QH, models for the returns RT, which is just the difference of logs. A, construct an adequate set of models for estimating and forecasting volatility. So we will do what we usually do, but pay attention that we will have an extra thing for our T gauge. This is already the answer, but I will move back here. So let's go. Same approach. The thing is, let me do this submods. We're putting these 2 models inside. And let's do then create just an empty list of T gauge models. Then we're creating the matrix as we usually do, where we save our information criteria. And it will receive 4 legs squared. So our ARMA, we're testing from 0 to 3. Then we're testing from 0 to 3 again. Then we will multiply by 2 cubed, which is Garch legs either 0 or 1, arch legs either 0 or 1, and threshold either 0 or 1. All right, so a few things going on there, and I will run it already while I'm explaining, because it takes for my computer somewhere around 2.5 minutes to process. You will see, and I'll explain what's going on there. So for our matrix, we're given this column names: PM, QM, AR, MA, this Garch, arch, then threshold, and our Akaike information criteria and Bayesian information criteria, as we usually do. Then we create this 0 guy. I receives 0. It's our index that will be showing which line we are in our IC ARMA T-Garch. Let's see if I can open it halfway through the processing. Nah, it doesn't allow, but that's okay. We will open when it's done. So the next thing is pretty interesting. This proc time, it takes your processor time. Let's see if it will allow us. Proc time, and we will save it in T0, and at the end of it we will print our proc time minus T0. So we take the processor time once again and subtract the previous one to say how many seconds it took for us to run this code, which is really nice. So make sure you run this one, and in sequence you also run this one. You could select everything, but it will make the calculation and show you how long it's taking. I think it's a nice thing to have, particularly when you're trying like massive ARMA models. It's a nice thing to look at. So let's go inside of our 4. 4, then we have 1 for AR legs, then MA legs, ARMA, Garch legs, arch legs, our Garch PQ, and then our threshold, right? First thing we do, since we started I with a 0, is to add a 1. So we're in the first line of the matrix. Then we will have IC ARMA T-Garch, which is our matrix here. And we will get all these 5 guys and put in the first, in the beginning of our row in the matrix, just saving which model we're analyzing first. Once again, when we're dealing with 0 Garch legs, 0 arch legs, we will be using our FEMA spec and our FEMA fit, not the UGarch ones, because they suggest that's how we should do it. And remember that we are using a try function. Why is that so? If you remember, we do it a try because sometimes the model is so complex or so bad that it gives up at a certain point, or it never finishes, or it returns an error. So what we're telling them is the following: try silently. So silent equals to 0 to do whatever is inside of our curly brackets, right? If you can't do it, move on. Like, stop sending warnings or anything. Just move on to the next one. So this is what we're telling. And the first step is just to do an RFEMA spec to create the model. This RFEMA spec receives a min model. So just the ARMA order PM QM, because as you know, this one is just for when Garch arch are 0, 0, right? Or Garch is 0, 0. So we do this and do our RFEMA fit with our model and using our data R and save it inside of our ARMA T-Garch estimate. All estimates will be inside of this one. Finally, we update our matrix with the 2 last things, which are information criteria, info criteria, which is the AIC and BIC, right? So that's what we take. We're taking the 2 first information criteria, the 2 first items, and saving it in position 6 and 7 of our row, or columns 6 and 7. This is when Garch is 0, 0. Then finally, we go to the most important, when Garch is not 0, 0, which is an else all of this is inside of an if, and then there will be an else. Also, another important thing, if I finished, so it opened. Also, we just do it when there isn't a threshold. I forgot to mention. So this is also inside of an if there's no threshold. This is how we run, because no such a thing of almost as threshold AMA for models with constant variance, which means we're not dealing with threshold if our gauge is 0, 0, right? Because as you remember, let's go back a little bit to our thing. We are modeling our gauge based on having an arch 1 at least. Look at here. So it wouldn't make sense for us to be doing it if we have a gauge 0, 0. No legs of arch. No arch legs, I think I can say. All right, so let's go. Next one. Now it's not gauge 0, 0 anymore. In the other cases, we're trying silent again. And then let's go. We're doing UGARCH spec and UGARCH spec to save the model. Now we have a min model receiving AMA order PMQM. We also have a variance model as we did last week, receiving a model with a GARCH, PH GARCH, GARCH legs, QH arch legs, and submods 1 plus thresh. How does this submod 1 plus thresh works? So if we're trying to model without threshold, this guy is 0, we're getting just the first item of our submods, which is an S-GARCH. So going back, S-GARCH, or you can see it here, the first item is S-GARCH. So we're just doing that. In case we want to model with a threshold, so when this guy here is 1, then we're getting the submods 1 plus 1 equals to 2, and then we get the GJR gauge. And this GJR gauge is how RuGauge package calls our threshold gauge. So let me see if we can open something here in the documentation. Let's go. That should be quite a relatively long documentation. Variance model, AP gauge, F gauge. There we go. JGR gauge is there. There's also T gauge, but you will see in the official solutions that T gauge here is slightly different than what we want. So we're using this one for our course. Okay, you will be able. Now, that's a little bit of a stretch, but if you want to go to the documentation we shared for RuGauge, you're able to have a look at, where is it? GJR. And you will see that they model our lambda as a gamma in here. And this is the indicator. This is our D, T minus J kind of thing. So this thing here is equals, let me flip some slides again, sorry, apologies for that, but you will notice that this looks relatively similar to this summation they have here. They're offering for many lags. We're just showing you just for the first lag. This is what's going on in a, let's say, more advanced mathematical way in here, considering a few more things. Okay. But well, anyways, this is what's going with the threshold. We just use the GJR gauge when we want to model for threshold gauge. Otherwise, we're just using this S gauge here. Okay, that is it. Like a little bit of a extensive explanation of how we're modeling, and then we finally make an estimation and save it inside of our list of estimations using the UGARCH fit that we used before. So our GARCH model that we just generated here, and the data of returns, and then solver equals to hybrid once again. Finally, we will get our matrix updated with AIC and BIC. So you use info criteria once again. Now, some pretty cool stuff that Eric did for this one, and I would suggest replicating if you can, or give it a go. I'm happy to help during consultations too, if you would like. But this is just a cat, and it puts down a little, let's say, we call it string of characters, but a little phrase. And this /r, it means it erases every time it writes again. So process AMA, then it says which AMA you're processing, 33. Look at this, open bracket, close bracket, the AR legs, MA legs. Then we concatenate also the tgotch 11. It's a little bit more complex than that, but it's being, sometimes there will be a T, sometimes there will not, and it's doing the same math that it does here, 1 plus thresh, and then call it arch. So you will see it flipping from gotch to tgotch here and there, and then the amount of legs we're considering, and then also it includes if there will be what amount of legs, space, let me see, tgotch also adds how much space you will have in the end. This one, why is that so? Sorry, gotch. It will be one space and no space later. I think it's just, this one is just an edit, just to make sure it erases the previous one. Nothing important. So when it's not gotch, it prints an extra space, and when it's when it's threshold or tgotch, it prints it doesn't print an empty space. Let me start again. When it's not threshold gotch, it prints the space. When it is, it doesn't. So it erases this last thing here. Otherwise, you would have a double close bracket. Nothing important for our theory, but this is what's going on. And finally, the proc time, it's doing it again and making a math here in order to tell us that it took actually much shorter than I thought. I don't think so. I think it was more than 77 seconds for sure. I think this is the important one we need to look at. It took this time that we're recording, and I think my computer is doing a few more things, over 4 minutes to run this model. So yeah, if you're trying with a lot of legs, make sure you're doing it when you have some time. Okay, so that's how we did our tgotch models. And let's go again. So we have our table here, the matrix recreated with 128 rows, each of our models described. So our AR legs, our MA legs, our gotch legs, arch legs, and if we're doing a threshold or not, if it's tgotch or not. And you will see these NAs here, we're avoiding it because we said when it's a 0, 0, don't do thresh. We're just making an estimation of threshold. Yes, pretty much that. Sorry for that. So when it's a gotch 0, 0, only consider the models without threshold, and that's what's going on. So if threshold is yes, so if we have a model 0, 0 and threshold is 1, we're not even running it. So saving a little bit of time there. Let's see if we had any error halfway through. It doesn't seem like the NAs seem pretty much spaced evenly. And then we have AIC and BIC. If you want to sort out which one are the best ones, you will see these models, then BIC, a little bit of different models. But let's continue going on there. So top AIC, top BIC. For AIC, we have usually a gotch 1, 1 as the best case, and we have thresh in almost most of them, just a few of them without threshold, and a variety of models with 3, 0, 1, and 2 AR legs, and 0, 3, 1, and MA legs, one with 2 here. Let's see with BIC, a little bit different. Once again, Bayesian information criteria, or BIC, has a heavier penalty when you have more legs and more coefficients. So you will see it favors mostly, like half of them are no threshold, and usually just one leg for AR and MA. But interestingly, all of them gotch for the top models, for both of them. So here we will get an intersect, and the intersect will have all of them with gotch arch legs, one leg each, gotch 1, 1, and then the rest of the things. And you'll see quite an amount of intersection in between the top 20 of each of them. And let's sort it out. Now here for our adequate set, it's sorted. So it's in order. Most of our models will have 0 AR, as you can see, 7 of them, and the rest of them, another 6 of them, will have 1 AR leg, and then just a few of them for 2 and 3. And in terms of MA, we kind of explore the range quite evenly, and gotch, all of them will be gotch 1, 1, and threshold, we have 0s and 1s quite evenly distributed too. Now, let's check our residuals, right? Instead, let me see if I have anything here that I'm missing. So we generated. Now we're going to check the residuals. So I'm not missing anything. Instead of doing our Young box test, we will be doing the ACF by hand once again. So first, we count the amount of models we have in there. You will see that we have 15 models. So if you print 15, then we will go, this is just the length of our adequate set, right? And actually the adequate index we're using as the length. And just to tell you once again, the adequate index will match which models we have in our adequate set with the models we had in our IC, on our matrix IC gotch, and it matches them looking at the first 5 rows. So the ARMA PQ, the gotch PQ, and threshold or not. Then we'll just measure how the length of this guy, which is 15, and that's how many models we have. So SACF T gotch. Once again, S is just for sample. This is just the ACF we use usually. T gotch, we create a matrix with the number of rows will be the number of models we have. So n mods 15. The number of columns will be 15. And once again, it's because we have all our 5 items specifying our model plus the 10 first legs. We'll see how much auto-regression we have in our legs. So let's go creating it. We gave it a name and we ran. Now we have an ACF T gotch model. Let me show you here in the slide what we're looking at. Look, so the 15 models in here, now apparently I have just 14. Why is that so? Adequate set ARMA. Just 1 second. If that's the case, I apologize. We'll be missing just 1 in my plot. Sorry. We SACF T gotch. Boop, boop. There we go. I missed 1. Oops. All right. So this is what we have. So ARMA PMQM, gotch PHQH, as you know, it's all 1, 1, and the threshold. And then it's the ACF that we calculated before for each of them, considering 10 legs. And you will see that all of them are very low. I think the highest we have is like minus 0.02 in absolute terms. I don't think there's any 0.03 around here. So I just put a green to everything. And what are we looking at? Once again, let me show you visually. These values for 10, particularly for the last one that we ran, all these values, it's like running an ACF. And I'll show you here how it's generated. First, it receives the first 5 rows. So pretty much PM, QM, PH, QH, and thresh. Then it will receive the amount of auto-regression we have in that leg, right? There's 10 values in here. And if we would plot this ACF, so where do we look for it? We will do an ACF, get our estimate. This estimate, we're using the index that we saved in here. And for our line, I. So in our for, we're going from I equals to 1, model number 1, until 15, our model number 15. And inside of that model, we're looking for the value Z inside of fit. So quite a lot of things, I would say. But let's go manually. See how we can find this value. The first one in adequate index, let me print this guide. The first item we have there for the first one is item number 7. So if I go to armatigage number 7, I can open it here, or I can open it there. Go to model number 7. Then inside of fit, there will be a lot of things, and there will be Z. These are the things we are running our ACF on. And then the result from the results, we're taking from the 2nd to the 11th value. And why is that so? Because the first one is always 1, which is our auto correlation function for leg 0, which is always right. So if we run, this is what you get. But most importantly, to have a visual of what we're doing, let me print it like that. Let me expand a little bit. So we are not worrying about these values in here because look at that. None of them is crossing the statistically significant value. Just this lag 0, which is equals to 1, as I said quite a few times, I would say. Apologies for that. But yeah, for the rest of them, all of them are very low. And that's what's happening here for all of our models. Okay, I just thought it would be nice to have a little bit of a visual of what's going on. And let me fix what I just changed it. And that's it. So we're okay. No autocorrelations are in our residual lags. So we're good with this modeling. Autocorrelations appear to be relatively small for all models. All right. Let's keep on going here. 2, draw inference on historic volatilities. So what we're going to do now is to plot our estimated volatilities. As we did last week, there's not much new here. So let's go little by little. First, we will get the titles. We was initiated with this rep. And then we will do the for. And you will see all the prints in here. And I always think it's nice to run first, so you can see the result when I'm explaining here. So all of this is just writing this line, right? It's quite a long code, be a lot of S character here. So title, I will receive, so from this large list of titles, the first one will receive a paste. So putting some text together, ARMA, open bracket. Then we take the first row, the first item in our row model, or it's the PM here. Then we take the QM. Then we take the PH, QH, 1, 2, 3, 4. Then we add a T in case item 5 is threshold. It's a 1. or if we're using modeling a threshold gauge. Otherwise, we don't add the t. So look how it moves with t and without t sometimes. But you notice the gauge legs are always 1, 1, as we know from our model. Also, pay attention how much it changes from one model to the other. It's pretty much the same. This one actually has quite a spike here. But in general, the format they are taking are very similar. All the 15 of them. So after all these lines of code to write the title, we will have this little plot here. First, it's date -1 again, because our R data has one less thing. Where is it? So many things. Now, it's one item less. Then we are getting the variance that was estimated inside of our fit of that model, the same thing that I just opened before, but we're taking the square root, because variance, it's the standard deviation squared. So when we're plotting it here, we're not exactly plotting the estimated variance, but the estimated standard deviation, all right? So pay attention that there is a square root in here. Then we're typing line, typing L for line, nothing in the X label. Y-lab volatilities, just writing it here. Y limit 0 to 0.08. We're forcing all our plots to have this Y limit, which is really nice because it makes, can you see these guys are not moving? It makes it fixed so we can compare one with another. And then finally, main is the title that we created with these lines of code, okay? So in conclusion, all volatility estimates generally look very similar. T-gauge versus gauge does not make a noticeable difference for fixed legs of both ARMA and gauge. However, larger ARMA models appear to be associated with larger spikes in volatilities when they occur. So larger, like 3 ARMA, 2 ARMA, 1, 3, pretty high here. I think the highest we have. 1, 3, 1, 3. I would say maybe the second guy is an exception for what we're describing here. But in general, higher legs are associated with higher spikes. Okay, and that's it in terms of drawing inference for our estimated volatility. That's what we can see. I just left a few prints in here, but there are 15. 3, draw inference on the existence of leverage effect. So in terms of AIC and BIC, we were happy with a few models with threshold. Also, when we look at the auto ACF plot, we were pretty happy with how the whatever was residual to that was behaving. But now we're drawing inference on the existence of it. So we're drawing a formal proof that there is a threshold, that using threshold would be interesting for this analysis we're doing. How are we doing that? First, since we have modeled already the T-gauge, it's quite straightforward to do this test. We're just doing a one-tailed t-test of our coefficient lambda. So we'll see if this lambda is statistically significant. Our null hypothesis is that lambda is equals to 0. So if we reject, we will say, okay, H1 for T-gauge probably will be larger than 0. It's the presence of leverage effects, right? So we should model using a threshold model. All right, how are we going to do that? We will extract the values here, and let's go to R so we can go line by line. See, for each of our models, another 4 here, going from 1 until n mods, we will get if our item 5 is equals to 1. Who is our item row 5? It's our thresh. So adequate set T gauge. Adequate set. Where is it? Whoops. Adequate set sorry. Let me run it first. Adequate set armor T gauge. We will just look at the guys who has which have 1 in here. And that's what that if it's saying. So let's get the lambda estimate. We'll get armor, fit, and coefficient. You will notice that when we create this Rugach models, they will call what we are calling lambda in our lectures. They call it gamma 1. And if you look, this is why they're calling gamma. You see, this is the Rugach documentation. So gamma is the same as what we call lambda. All right. So gamma 1. And then we're taking the T value from gamma 1. This is what we're printing in here. So for the first model was an armor 00, T gauge 11. All of them are T gauge because we're filtering only for the ones with presence of threshold. And we're taking this value from there, 0.02. Then we're taking the T value, which is 4,000, which means, I want you to think about it. Is 4,000 T value a very high P value or a very low P value? It definitely looks like a very high T value, right? And if you remember that they go opposite ways, this would be a very low P value. So we're going inside that, getting these two guys. If I would show you once again, let's try to look at this 3011. 3011 is our 3011. It's our model 15. Our model 15. I'm going all the way back. 3011. Oh my God. Where is it? I filtered. Even worse. I would not know. 3011 in our adequate set. Where is it? Just 1 second. This is what I want. Would be our model 104. Where are our estimates? Are here. 104. It's down here. And then we're opening fit. And inside of fit, what are we getting? We're getting the coefficient. So which coefficients are we getting? We're getting the gamma 1. Let's go there. 104 coefficients. Gamma 1. 0.01133357. Kind of 0.01. They're not printing a lot. T value. T val. Not here. Once again, T val. Gamma 1. 4184.124. 4184.12. There. Right? Oh, I'm glad it was the right one. Could be the wrong one. Who knows? But yeah, that's how it's finding inside of our estimates. A little bit of, I think it's interesting to show you guys how it finds. Probably when you're doing your assignment, you'll be able to replicate without knowing in depth where the value is coming from. But I think it's worth it to show. Then, by the end of it, we are printing it. Once again, this is how we generate those lines. We're printing the title, and this is a smart thing from Eric. He saved these titles before when we were running it here, so we can use it again, reuse this list of titles. So if I run these guys, there will be the titles for all the models. But pretty much we're using the title for that specific model in our adequate set, adding a little bit of text, lambda hat equals. Then we take the value, we're rounding it to 2 decimal places, and then the T value that is written in here, and rounding it to 2 decimal places. And that's it. That's what's going on for our C. What we're doing is, once again, let's go back. These values, we are rejecting that lambda is equals to 0 or gamma 1 is equals to 0 for all of our models. So in all of them, we are detecting the presence of leverage effects, which means that negative shocks are different than positive shocks, right? And in this case, specifically, negative shocks are greater than positive shocks. Or negative news increase volatility more than positive news. I hope that's one way to think about it. That's it. So we reject for all models. Okay. Well, this was C. Finally, last item for our question 1, D. And I promise question 2 will be faster because we've been through everything here. Question D, forecast volatility for the 4 trading days past the end of the sample. So now we will forecast volatility, which might sound exactly the same as forecasting our estimate or point estimate as we did before. But it's important to keep in mind that we're talking about volatility. Okay, so you will notice a little bit of the difference. Let's go. To do this forecast, very simple here, we will be using UGARCH boot for Bootstrap. It is pretty rigid in terms of the format we have. So univariate Garch forecast via Bootstrap. And we get our models, which models we're using our adequate set, and we're using the method partial. Okay, this method partial, there is a method called full, but it takes really long to process. So we'll just do the partial one to generate partial confidence intervals for our forecasts. And look at this. Think about it. We're not forecasting the point, but how much volatility we had at that point. So this is sigma, and so standard error, not sigma squared, which would be variance. So standard error would be 0.008, maybe 85 around here. Just one time period after 0. Then for the second one, it would still remain, and generally the forecast will remain at the same level. Does it mean that the price of the stocks not change? No, it doesn't mean it's not changing. It means that our forecast is for the variance to continue the same. So it means when you look at the change, it should continue in a same pattern. So if the stock market goes down, it goes down together. The stock market goes up, it goes up together. I hope that makes sense. But it varies in that amount. Then we have a confidence interval. Then we have a bootstrapped here, which changes a little bit, increases a little bit, not too much. And then we have some intervals. These little dots are talking about these guys in here. So the first one would be the 5%. And the last one will be the 95%. So included in this is the 90% confidence interval. So from 5 to 95, so 90. In between the second and the third one, 25 and 75, it's just a 50% interval in that, okay? But another thing to think about this one, I'm spending more time interpreting it because it took me longer to understand what this one's talking about. You will notice that the upper boundary of our confidence interval tends to grow more than the lower boundary. And why is that so? One thing to remember is, once again, we're talking about variance. So there's nothing that goes below 0, right? It's variance. It's particularly, it never gets to 0 because usually we're looking at financial amounts or economic amounts, and it tends to have some variation, right? It's not stable like a single line, same value forever. So you would understand that this thing here going down, it happens, but it happens less often than going up, having like some spikes in volatility and then coming down. It's already a low value of for standard deviation, so coming lower than that would be relatively rare. Also, what we can say for our forecast in terms of sigma is that it can be, there's a 90% chance that it's in between 0.08 and 0.10, right? Let me try to click many times back and try to look at our estimated standard deviation here, because it's not variance because we took the square root, so standard deviation. And you will see that it is estimating for this model. Is it the same model, I think? It's estimating the variance will be running around here, which is pretty high. In here. Okay, the value that we have there. I suspect, yeah, this one here. So this is the variance that should continue happening. I'm not sure if I'm considering the wrong amount of zeros, but 0.08. Let me go once again. Yeah, I apologize. 0.0, no, 0.08 in here. 0.008. Okay. Oof, now that makes sense. Sorry. So we are forecasting that it will, after this point, it will continue somewhere in here, 0.08, which is there. Oof, for a second, I thought that looks wrong. So our forecast is keeping variance around here. Okay. So I apologize for a little bit of the confusion. There was an extra zero there that I didn't account for. And that's it. You will notice there are subtle differences between the volatility forecast generated by different specifications. So when I move, it moves a little bit, but not too much. You will see they're all around in between 0.008 and 0.010. Okay. But all agree that volatilities across forecast horizon will remain well below the levels estimated around 2005 and again in 2008-9, which are those higher volatilities we got here, 2005, and here between 2008 and 9, post global financial crisis. That's it. So this is what we did for T-gauge and threshold gauge. How to estimate it, how to detect the presence of these leverage effects, and how to forecast, see our estimated volatility and forecast future volatility. Now, we're going to move to the next one, which is going to be gauge in mean. Let's go there. Consider a class of gauge M or gauge in mean or arch M sometimes models for returns RT with one arch leg and one gauge leg. First, realize that now we're just looking at gauge 1-1, so we will make our estimates much quicker because we don't need to run for each of the possible models. And then we're looking at our gauge in mean. And what are we talking about here? Gauge in mean starts looking at the fact that our volatility is not only impacting the volatility itself, but also impacting the mean of our model. And why does that make sense in finance? A lot of times, you have the option of buying totally secure bonds with, and that's the risk. You take like a riskless asset, and that offers some return per year, right? Some percentage per year. Why would you buy something that offers you an extra risk? You only sell your bonds to buy something that offer an extra risk, and extra risk is not return. Risk is the volatility, like the chance of getting more return or less return, the volatility. Why would you buy that? Given that your bond has, let's say, zero volatility, it's kind of guaranteed payment after you bought it, you will receive that amount. You would only buy this extra, this riskier asset if you're going to get some extra returns. So you taking on risk because you expect to have extra returns. And that's exactly what we're looking at here. So if there is an extra volatility, so I would expect my returns, the mean, to be higher too. And that's where you find this balance. And that's what we call, where is the risk premium thing? Yeah, pretty much a risk premium, higher expected return. No, okay, it will be written later. But we're talking about our risk premium. So for extra risk, you're receiving a premium return. All right. This is where we're modeling it. Will be this little delta. Once again, Rugart models with something else, but will be this little delta. And we put a square root of our HT as we had for our residuals. But the model is in here. All right. This is what's going on. So it's, once again, it looks like an MA model with error squared and a summation here. But yeah, that's an arch in mean. That's why it's called like this. All right, enough theory. Let's do it. Construct an adequate set of models for estimating the risk premium. Let's go to R. All right. We're creating a list. Once again, then the matrix, as you know, just our 4 models, we're looking at ARMA from 0, AR from 0 to 3 lakhs, MA from 0 to 3 lakhs, Gotch 1-1. So we don't need to change it. We'll straight specify 1-1, and then we're putting the presence of this risk premium 0 or 1. Okay. So that's why we have a 4 squared for here, and times 2, which is 0 and 1. So matrix call names 1 proc time, and then I'll run these 2 guys here. This should take just some seconds, maybe 30 seconds, but let's go. So we start I equals to 0, the proc time here to start counting our clock, and the force, as we did before, I increments for 1. Then we're saving the model, P, Q, and M. Then we're doing a try. Now we don't need a try for PM, PH, and QH equals to 0 because we're already assuming it will be a Gotch 1-1, right? We can go straight to our UGotch spec to generate our model, and then our UGotch fit to save, to process the model and save. Inside of the spec, we get the mean model ARMA PQ, depending on what specification we're giving, and arch M, look at that, how we specify. Arch M receives M. So we'll receive a 0 or a 1, depending on what we're looking at. So then we have our Gotch. Our variance model says that it will be a Gotch 1-1. So we have, our model. Then we come here and specify will be a Gotch M mod using R, and a solver would be hybrid. Okay, that's it. And finally, we get the information criteria, AIC, BIC, and save it in column 4 and 5. You will see we are doing the process ARMA running here in the bottom. You probably saw it before, and it took 43 seconds this time to run the whole thing. It works exactly the same as we did in the previous one, so there's no need for too much explanation in this one. Finally, it calculates proc time once again and subtract the previous one and gives us this answer we have in here. All right, so we have quite a few guys inside of our IC gauge, 32 in total. And then now we're going to take the top 20 AIC, top 20 BIC, and see what is the intersect, right? So 1, 2, 3, we have an intersect. Finally, our adequate set will be just in a range of these guys, of this one, in, so you see as data frame here, and we're ordering it in terms of P, then Q, then M. So after we run this one, we get this nice list of models. So 0, 0, 0, which is still gauge 1, 1, but all zeros, and the rest of them here. Then finally, we do a match just to get the positions of our models in our huge, big list of estimates. If you're curious to see, we have 32 estimates, and we're using 1, 2, 3, and 4, then 7, 8, 9, 10, 11, 12, 13, then 17, then 19, 26, and 29, right? Finally, we're going to check the residuals, and will be the same process again. Number of models gets the length of our list of positions here. Then we will do an SACF. Gauge M will be the name of our new matrix. And this one will have just 3 because we're just specifying our ARMA lags. And then if it has mean or not, this little M here for our risk premium. Run, and then run the full. Oops, run the full. In that, we set the first 3 columns to get the model, and then the other one. Once again, we'll get the ACF of that guide. This time, I don't need to show you how to get to this value once again. If I would print, this is what we do in our table. Oops. This is how our table looks like. Probably loads of very non-statistically significant error. And that's what you're going to see. This table, very low, very autocorrelation in the legs. So all green, once again. The highest must be 0.02 and something. So still pretty low. And that's it. So we're happy with the models. Autocorrelations appear to be relatively small for all models, right? We're happy with this. How many models? This 15 once again that we're running with. All right. B, draw inference on historic volatilities. The process will be the same. We have, we start a table of titles, a list of titles. Then we will generate the titles again the way we did before, but now instead of T gauges, we have gauge and gauge M. So you see gauge and gauge, the M appearing there depending on the model. And once again, look, they look pretty much the same. There is a little bit with the spikes, but not a huge difference. What else? So I think the title, we're good with how it's being plotted. And the plot, once again, date -1, taking the square root of ARMA gauge M estimate, fit, and variance. So square root of variance is the standard error. Type line, volatility, blah, 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 fix from 0 to 0.08 in here. And then the title, the main, receives this title, gauge MI. All volatilities estimate generally look very similar. As you see, we're moving throughout them, and they change very little. Just a little bit of the spikes reach a little bit higher or lower, but not a lot of difference. Periods of high volatility match up with those estimated using T-gauge models. So pretty much the same as the previous modeling, maybe a little bit of difference. But yeah, that's how we draw inference on historic volatility. So once again, we have historic inside of the time frame we have observations for, and then we have forecasting, which talks about the future, right? It's a good thing to keep in mind, not to have those things mix up. So now we're going to draw inference on the existence of a time-varying risk premium. So a risk premium that is changing depending on what we look at. We will use the same process we did for the presence of leverage effects. So we will have an I running from 1 until any mods. And in there, we will only test the ones where the M is equals to 1. So Garch in mean, we're testing for Garch in mean. So the arch M estimate gets this arch M thing coefficient and T value. Once again, so we have this last guy here. Let me go through this one. It will be the one in position 29 of our Arma-Garch M estimate. Position 29. Arma-Garch M estimate. Position 29. We have fit. Then we have coefficients. Then we have Arma. Where's the Arma thing? Am I missing it? I might be. Okay, fit coefficient arch M. 29 fit coefficient arch M. Where is it? Am I not looking at the right one? Maybe. Okay, well, it's probably happening here. Maybe the last run of my I wasn't a mean value. So let's look at the previous ones. Let me print the whole thing. Before 29 was 26. Which one is model 26? Not this. I see it's Arma-Garch M. 26. Yes, 26 is an M. So probably the last one we have here is model 26. Let's go again. Second try. 26 fit coefficient. Yeah, there it is. Arch M 0.0513. So 0.05. And then we go to our T value. And arch M T value 605.75. 605.75. We found it. So in this model, as you can see, once again, it's a huge T value. And it is for all of them except for this one. But this one's still statistically significant, still P value smaller than 0.05. So all of our models, for all of the ones we estimated with a mean, we are rejecting the null hypothesis that this delta, this little delta in here, is equals to 0. So there is a time-varying risk premium for all of these models here that we modeled. Okay, so this little delta, the only difference is that it's called arch M in the real Garch package. But yeah, this is it. This is how we draw inference on the existence of time-varying risk premium. Finally, last part, forecast volatility for the 4 trading days past the end of the sample. Look at that. Once again, we're doing a UGarch boot, Arma, blah, 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 all the thing, and doing method partial. And you will see that forecast stays the same, 0.008. So pretty much the same value, a little bit higher, I would say. So closer to 0.009 for our Garch mean instead of the threshold, including sometimes passing the 0.009. And look at it, it's increasing in here. So the forecasted volatility with a slight increase and definitely higher than what we had for our T-gauge models. Okay, 0.009, somewhere in the middle here. So going around here. All right, and that's it. Once again, if you want to get the 90% interval for the 4th day, it would be between this little dot and the upper dot, because the first one represents the 5%, the other one 95%. So 90% chance that the variance will be between 0.008 to something like that and 0.01. That's how we interpret this plot of variance or volatility. It's actually not variance, it's standard deviation, but yeah, I think you get what I mean. And that is it for today. So today we construct some models for a threshold gauge errors. We construct adequate set of models for our gauge in min or arcm components. We used to draw inference on the presence of leverage effects for our T-gauge and the presence of time varying risk premia for our gauge in M, arcm models. And finally, we used R to estimate and forecast volatilities based on models with T-gauge errors and gauge in min components. And that's it for today. If you guys want to talk about the assignment, feel free to stay after I end the recording. But good luck in your last days of the assignment, and I'll see you next week. Thank you. Bye.